Okay, welcome back. Unfortunately, I did not record the audio the first time around for myself, although I got all of the students, so I got all of you guys. So I have Miss Vivian with me, who's here to help me correct any simple mistakes I make while I try to go through everything we did today as fast as possible. Um, we are in the middle of a test in pre-calculus, so I'm going through some pre-response questions from other AP examinations from Calculus AB and Calculus BC, trying to help figure out what courses that you guys want to take later. So I'm going to go over the objectives in a second, but I do want to talk about what's going to happen on Wednesday and Thursday first. So on Wednesday and Thursday, I'm going to start doing one-on-one interviews with each of you. So each interview will take about 5 minutes. We'll talk about course selections for next year. If you're in grade 10 or 11, we'll talk about anything that's left to do as far as college prep goes, if you're grade 12. As well as the final exams and any quarter 4 grade stuff that we need to talk about. So it's 5 minutes per person. It's going to be fast, but hopefully we'll be able to get the recommendations for your course selections in after talking with you. I am going to recommend that you go to Calculus AB if you have a B or higher in quarter 3. I'm also recommending that you go to Calculus BC if you've got a 90 or higher in quarter 3 and you pass the midterm. Normally I test into these courses. I've kind of been doing that throughout the year here in pre-calculus. So you guys have been taking a handful of long-form pre-response questions. Those were pulled directly from a Calculus AB exam. So I have an idea already. I have tested most of you already for who's ready to go into Calculus BC and who's not. So we'll be talking about that individually. AP Statistics is also an option. We don't have any non-AP options after this class. I'll talk to you and see if it matches up more with your major if you're in grade 11. If you're in grade 10, then I'd like you to jump into Calculus BC if you think you're ready, and then take AP Statistics in grade 12. But the key is to have a math every year when you're in high school. We do have students this year who have been trying to apply to Japanese and Korean universities and are not getting into the universities that they want to get into because they skipped a year of math. They just chose to take 3 years as the minimum we require at SLAS instead of taking 4 years, but not taking that 4th year hurt them when they tried to take their entrance exams for the universities in Japan, or just outright took them out of the running for a couple of the Korean universities. So please take 4 years of math. It looks much better in your transcripts and it keeps you fresh for just basic algebra stuff for your SAT and your entrance exams. So I've got time slots that are here for our class 2. Please make sure that you're ready on time. If you can't make it, let me know and I can reschedule with you. Our objectives for today, we're still working with integration and related rates. So we'll be looking at interpreting the meaning of some accumulated rates of change and derived rates. Okay, so that brings us to our problem. We're told that the rate at which rainwater is flowing into a pipe, which is given here, RT, in feet per hour, over the course of an 8-hour period. We're also given the rate at which water is draining out of a pipe in dt, also in cubic feet per hour, and the amount of water that we started with. We started with 30 cubic feet of water in the pipe at t equals 0. So with those 3 pieces of information, I'm going to change the colors on this. I've got our RT, which is the amount of rainwater that is coming into the pipe, or how fast the water is coming into the pipe rather. So it's a velocity, a speed in cubic feet per hour. dt, how fast the velocity, the speed, the cubic feet per hour that water is draining out of the pipe, and then we started with some water already in the pipe. For part A, I want to know how many cubic feet of rainwater came into the pipe during the 8-hour interval. So if I already have a rate, a velocity, and I want to get to an amount, I could integrate. If I integrate this rate in feet cubed per hour in terms of time, so that would be the integral of RT in terms of time, then I would be able to multiply our units together. RT is currently in feet cubed per hour. dt is currently measured in a change in hours. So my units would cancel and I would be left with cubic feet of water that came into the pipe. Okay, so that gives us our answer here. If I want the amount of rainwater that entered the pipe from t equals 0 to t equals 8, I could integrate from 0 to 8 of RT dt. Now, we have not done this yet, but I do have an equation here that we'll need to integrate using a graphing calculator, so I'm going to show you how to do that. Okay, so here I've got our graphing calculator. I'm going to clear everything out from the previous class and start over. I am in radians. Okay, so the first thing I'm going to do is I'm going to type our equations into the calculator. So starting with RT, I'm going to hit y equals, and we'll type in RT here. This is 20 times the sine of t squared divided by 35. And then I've got dt, the rate at which water is draining out of the pipe, is negative 0.04 t cubed plus 0.4 t squared plus 0.96 t. Okay, so what we want to do is we want to integrate RT, so that's my y1, from 0 to 8 in terms of time. So I'm going to hit second quit, and our new function for today is function integrate, which you can find under the math function. So if you hit math and scroll to the 9th option down, you'll see fn integrate. The equation takes 4 options if you've got an older calculator. It takes an equation, comma, a variable, comma, a lower bound, comma, an upper bound. So 4 arguments: equation, variable, lower bound, upper bound. So our equation is my RT. So I'm going to paste that in. Variables, y variables, function y1. I just pasted in the equation RT that we typed here in y1. 20 sine x squared over 35. Second quit brings back to the main menu. So equation, comma, variable, I'm integrating in terms of x, comma, from x equals 0, comma, to x equals 8. Equation, variable, lower bound, upper bound. And if I hit enter, our calculator will integrate that for us. So if I integrate 20 sine t squared over 35, I'll get 76.57 feet cubed. Again, for our units, since we integrated, I will multiply our units for y by our units for x. And so that's our units for RT, cubic feet per hour, times my units of t for my change in t, would give me cubic feet for my units. 76.57 cubic feet of rainwater entered the pipe during the 8-hour interval. Any questions on part A? Okay, part B. I want to know, is the amount of water increasing or decreasing at the time t equals 3 hours from the start point, and then give a reason for the answer. So if I'm looking for is the amount of water increasing or decreasing, I'm looking for what is the change in the amount of rainwater doing at the time t equals 3. So that's the derivative of my amount at 3. Well, my amount is changing because of the rate at which water is coming in and the rate at which water is going out. So I could say the speed at which the amount is changing in cubic feet per hour is the cubic feet per hour of water that come in, RT, minus the cubic feet of water that go out, DT. RT for rain, DT for draining. So if I plug in 3 into these functions, how fast is the water coming into the pipe at hour 3, minus how fast is water draining out of the pipe at hour 3, I'll get how fast is the amount of water total in the pipe changing at hour 3. Which again we can do in the calculators. This is another new calculator function. If I want to plug in a value into my equation, we can do that using parentheses. So just gonna hit variables, y variables, function y1. I want to plug in the time 3 into our function. So if you just put some parentheses, this is function notation, just like f of x. If you wanted to get your y value at 2, you would type f of 2. This is y1 of 3. I'm not multiplying, I'm plugging 3 into my equation. So in this y equals for y1, I'm going to replace this x with 3. So if I hit enter, I get 5.09-ish for RT at 3. Okay, I'm going to do the same thing for dt at 3. is 5.4. So right now, the rate at which water is going into the pipe 3 hours after we started is about the 5.09 cubic feet per hour. And the rate at which water is draining out of the pipe is exactly 5.4 cubic feet per hour. So if we subtract that, then the rate at which water total is changing in the pipe is 5.09. That's the amount coming in. This rate at which water is coming in minus 5.4. The rate at which water is going out is negative 0.39 cubic feet per hour. My change of water in the pipe at 3 hours after we started. Any questions on B?
That's clear.
Part C. So the next thing we did was we created an equation for the total amount of water that was in the pipe, and then derived it. We needed to figure out when the water was at a minimum. So in general, when you're looking for a minimum, you would take your function, derive it, set it equal to 0, and solve for x to get the critical points. What we're doing there is we're setting the slope, that's the derivative, equal to 0, which will give us any points that could be a relative minimum or maximum. So points where, compared to the points around it in the function, we're at a large point, a peak, or a trough, a minimum, if the slope is 0. However, we also need to test the start point and the end point if I'm looking for the absolute maximum or minimum. And the reason why is because it's possible, like this graph that I just drew here, for the start point to be less than a relative minimum or the end point to be higher than a relative maximum. We don't have to have the slope equal 0 if we're a maximum or a minimum for the start point or the end point specifically. But for any other point, we would have to have a slope equal 0 as long as our function's continuous and differentiable. So I'm going to create our equation for our amount. I had some amount of water that was our starting amount of water in the pipe, which we were told was 30 cubic feet of water at t equals 0. So I started with 30. Then I added some amount of water that rained into the pipe. Since they gave us a rate at which the water comes into the pipe, here in yellow, what we can do is we can integrate that amount. So if I integrate the rate in cubic feet per hour in terms of hours, I'll end up with cubic feet as an amount of rainwater that came into the pipe here in blue. And then I'm going to subtract this dt, the rate at which water is draining from the pipe. If I integrate it in terms of time, will give me the amount of water total that drained from the pipe from 0 to t. So that's from 0 to any time we want. Basically, how much rainwater was started in the pipe plus how much rainwater we added to the pipe minus how much rainwater we drained from the pipe gives us the amount of water in the pipe right now at any time. Any questions on our setup?
It's very clear.
Okay, so if I derive this, if I derive a constant, I get 0. If I derive an integral, I would integrate this to get, I'll call this lowercase r as my integral of RT, plug in my upper bound and subtract my lower bound. And then when I derive it again, I would have chain rule. So this would be r prime, which is capital R, t times chain rule, t prime, minus capital R of 0 times 0 prime, but 0 prime is 0. So when I go to derive this, I'm going to get RT, my original rate, times t prime, which is 1, or RT. When I go to derive dt, I'll end up with dt, the rate at which water was draining from the pipe. So what this says is the amount of water, the rate at which the amount of water in the pipe is changing. So that's my cubic feet per hour for the whole pipe, not just going in or going out, but both. Is going to be the rate at which water comes in minus the rate at which water comes out is the rate at which the water is changing total. If I set that equal to 0, so that's my slope of the amount we're setting equal to 0 and solve for t, then I will get any relative maximums or relative minimums for our function. There are two ways you can do this in your calculator. You could either say if RT minus dt is 0, then RT equals dt. So you could graph RT and dt and calculate the intersects. That would look like this. I have RT and DT already in the calculator. Right now, looking at what I should set my window to, we're only looking at times from 0 to 8, so my x value should be from 0 to 8. I'm going to put my scale at 1, so each hash mark represents 1 hour. For my y values, RT is 20 times the sine function. Sine can bounce between 1 and negative 1. So the maximum would be 20 times 1, and the minimum would be 20 times negative 1. So this could go from negative 20 to positive 20. So if I graph our functions right now, I'm going to hit y equals and change this graph to dt will be in bold, so I know which one's which, and hit graph. So here's our function that's not in bold, so that is RT, the rate at which water is raining into the pipe. And here's our graph that is in bold, so that's DT, the rate at which water is draining from the pipe. If there's any point along here, I know this is a little bit hard to see right now, so let's go ahead and zoom in a little bit, just so we can see what's happening to our graph. I'm going to zoom box. Zoom box means when I press enter, I can start to draw a box with the arrow keys. When I press enter again, that box will become the window so that we can see what's happening with our graph. So I'm going to expand this just a little bit and make our window equal to this box that I'm drawing right now, so that we can see if these functions cross a little bit easier. Okay, and that's a little bit easier to see. We can see these functions do cross. My scale is still 1, so this is hour 1, hour 2, hour 3. A little bit after hour 3, our functions cross. If I want to know exactly where, I can hit second, calculate, and intersect. It's going to ask me for first curve, second curve, and a guess. And that's because I could have 3 functions graphed, and it needs to know which 2 you want to cross. So I'm going to say, this is the first function I want to cross. Enter. Should bounce to the next function. This is the second function I want to cross. I'm going to hit enter. And then a guess. So as long as I'm closest to the intersect, it's going to guess whatever closest intersection is to our cursor right now. So if I press enter, here's our closest intersection is here at 3.27-ish. Is our time when RT equals DT. Okay, the other way we could have done this, I'm going to break out, is if I hit y equals, I'm going to turn off our graphs of RT and DT and graph a new function 3, which is RT minus DT. And instead of calculating an intersect, I can just calculate whenever this function equals 0. And I should get the same answer. So I'm going to do that really quick. We'll set our window to, I just need to see around 0. So I'm going to say from negative 5 maybe to positive 5. And I'll look again from x equals 0 to x equals 8. And we'll graph that. So here's our function of RT minus DT, and you can see after 1 to 3 hours, a little bit after 3 hours, we hit 0. If I want to calculate exactly where, I can hit second calculate, a 0. It's going to ask me for a left bound, a right bound, and guess. For the left bound, I'm going to move the cursor over to the left of the 0. You can see I'm left of the 0 because my y value is negative, hit enter. Move my cursor over to the right of the 0. I know I've passed it because my y value is positive, hit enter, and my guess will give me the closest 0 to that point, which is here at 3.27. If I want to use that but not round, I can hit second quit x store alpha a. So now if I want to use that in any equations, such as 2 times a, I can do that without having to worry about any rounding errors. Any questions so far?
Great.
Okay, so right now I've got a time that is a critical point. That means when the derivative is equal to 0. The only time where our derivative was equal to 0 was at 3.27 hours. So that's a possible minimum of our function, but I also have a start point and an end point. So what I'm going to do is I'm going to plug, let me get the calculator out of the way, I'm going to plug 0, my start point, 3.27, our critical point, and 8 into our amount equation here to figure out what the y values are. And then the lowest y value should be the minimum. So here I've got the times of all possible minimums in this column. And we're going to get the amounts, our y values in this column, so it'll be easy to see which one is the smallest. Okay, to do that, well, the first one we don't actually need to calculate because at t equals 0, we were told there are 30 cubic feet of water in the pipe. So the first one we already know is 30. The last two we do need to calculate. So to calculate this, I'm going to plug in to this equation. our t value of 3.27. So this is 30 plus the integral, math 9, of our equation RT, which for us is variables, y variables, function y1, in terms of x from 0 until our t value, which for us is a, is the value we stored in our calculator. That is 3.27 without rounding. Okay, then I want to subtract another integral, math 9, of dt, so that's variables, y variables, function y2 for us, in terms of x from 0 to a. Okay, so I've just plugged 3.27 into our amount equation, AT. That gave us 27.965, 27.96 feet cubed. Okay, I'm going to do the exact same thing, but plug in 8. So if you hit second entry, that repastes everything that you typed. I'm going to change all of these A's to 8. And we'll do it again. Okay, it gave us 48.54 cubic feet. So what this means is the total amount of water in the pipe, at the time t equals 0 was 30 cubic feet of water. At 3.27 hours after we started, we had a minimum amount of water in the pipe, a relative minimum. That was 27.96 cubic feet of water in the pipe, because it was raining, but we were also draining some water. After 3.27, though, the amount of rain that was entering the pipe was entering faster than the speed at which we were draining water from the pipe. So my amount started to increase. And so at t equals 8, we actually had more water in the pipe than what we started with. So to answer the question, at the time 3.27 hours after we started, the amount of water in the pipe is at a minimum. Any questions on what we did?
No question.
Okay, last one. This looks a lot more complicated than it is. We're told that our pipe can hold 50 cubic feet of water before it overflows. And if we keep going beyond the 8-hour interval, water continues to flow at the same rates that we were given before. We want to write but do not solve. We don't have to do any math. An equation involving one or more integrals that gives the time when the pipe will overflow. So we were told the pipe will overflow if the amount equals 50 cubic feet of water. So whenever AT equals 50, we overflow. Well, we already wrote an equation for the amount here. So I'm just going to copy that over. 30 plus our integral of 0 to t of RT minus our integral from 0 to t of dt in terms of time should give us the amount at any time we want. And the time that we want to overflow is w. So I'm going to plug that in for our variable for time. The time that we want when this water will overflow when the amount is equal to 50 is w. And because we didn't need to solve the equation, that's it, actually. We just needed to set it up. Okay. Any questions on anything?
No question for that.
Awesome. Thanks for help.